Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
I want you to try something with me. It's a mental exercise I do sometimes when I can't sleep.
Oh boy. Okay, I'm listening.
Imagine you are standing in the middle of the Great Basin Desert. Just you, the silence, and the ground beneath your feet. It's midnight, no moon. You look up.
I know this view. It's one of the most humbling views on Earth.
It really is. You see the Milky Way arching over you, that dense river of stars. You see Jupiter, maybe Mars, but mostly, if you're being honest about what your eyes are actually registering, you see black.
Darkness. Sheer darkness.
Right. Vast, crushing darkness. And our brain has a very specific default setting for interpreting that darkness. We look at the space between the stars and we think, that is empty.
It's the ultimate intuitive assumption. I mean, it makes perfect sense. If I take a box and I pump out all the air, sweep out the dust, block the light, and, shield it from magnetic fields, I have an empty box. I have nothing.
And for most of human history, that was it. That was the assumption. The void is just, it's the absence of stuff. But today, we're going to take a sledgehammer to that intuition. Because it turns out that empty box doesn't exist.
It really, really doesn't.
We're going to explore the quantum vacuum. And the headline, which sounds completely contradictory, is that nothing is actually something. In fact, empty space might be the most active, chaotic, and energetic thing in the entire universe.
It's a foundation of reality. That's not an exaggeration. It's not just a backdrop for the action. It's a seething ocean of activity that shapes atoms, that evaporates black holes, and might even be responsible for the Big Bang itself.
So if you could actually see what's happening in those dark patches of the night sky,
yes,
you wouldn't see emptiness at all.
No. You'd see a riot.
A riot in the void. I love that image. But before we get to the chaos, we have to, respect the history here, because for a long time, the smartest people on Earth, we're talking Newton, Galileo, they were firmly on Team Empty.
Oh, absolutely. And it makes sense, doesn't it?
Mm-hmm.
This is what we call the classical view. Think about Isaac Newton. For him, space was a stage.
A stage.
A passive wooden stage. The actors were the planets, the stars, the apples falling from trees. Mm-hmm. They moved around on the stage. They bumped into each other. Gravity pulled them this way and that. But the stage itself,
it didn't do anything.
It did nothing. It was just the container, an inert, passive background.
So it was just there. If you kicked all the actors off the stage, if you somehow removed all the matter and energy from the universe, the stage would just sit there, existing, but completely dead.
Exactly. In classical physics, and this includes Maxwell's incredible work on electromagnetism later on, the definition of empty was basically a mathematical zero.
No particles.
No particles.
Well, that's no radiation.
Well, it's no radiation. And that equals a zero field value. That equals truly fundamentally empty.
And to be fair, this view worked. It worked beautifully for centuries.
It did. It predicted planetary orbits with stunning accuracy. It let us build bridges, design machines. There was absolutely no reason to doubt it.
Until the 20th century showed up and decided to ruin everyone's simple, organized life.
Or make it infinitely more fascinating.
Depending on how much you like linear algebra, I guess. So the quantum revolution happens. What was the specific thing, the smoking gun that killed the idea of the empty container?
It wasn't one single discovery, but it all hinges on one fundamental rule, a pillar of the whole theory.
Yeah.
The Heisenberg uncertainty principle.
Okay, I know this one. Or I think I do. This is the you can't know where a particle is and how fast it's going at the same time rule.
Right. That's the version most people learn in school, and it's absolutely correct, position and momentum. But the uncertainty principle is actually a much deeper, much broader statement about the nature of reality itself.
So it's not just about position and speed.
Not at all. It applies to other pairs of properties, too. You can think of them as complementary variables. And the one that completely breaks the concept of nothing is the relationship between energy and time.
Energy and time. So you can't know the energy and the time simultaneously. That sounds a little more abstract.
It is, but think of it like photography. If you're trying to take a picture of a fast-moving car, you need a really, really fast shutter speed to freeze the action.
Right. If the shutter is open too long, the car is just a blur. If it's open for a millisecond, the image is crisp.
Exactly. But there's a trade-off, isn't there? To get that crisp, frozen moment, that is, a super precise measurement of time, you have to let in very little light. You lose information about the scene, about the energy of the photons, because your window is so short.
Okay, I'm following.
The uncertainty principle is like the ultimate unbreakable shutter speed limit for the universe.
So how does that apply to energy?
Well, the formula states that the uncertainty in energy, we call it delta E, multiplied by the uncertainty in time, delta T, must be greater than or equal to a specific tiny number half of Planck's constant.
Which is a famously tiny number.
It is incredibly tiny. But the crucial part is that it is not zero. And that distinction, that tiny non-zero value, changes everything.
Okay, so what does that tell us?
It tells us that nature forbids you from knowing the exact energy state of a system if you look at it for a brief enough window of time.
So if I try to take an incredibly fast snapshot of empty space,
the image of the energy becomes blurry. It has to. The uncertainty in the energy explodes to compensate for the certainty in the time. It means that on very, very short timescales, the energy of any specific point in space must fluctuate.
Hang on, must fluctuate? You don't mean it can fluctuate.
No, I mean must. It's a requirement. Nature literally does not have a zero setting that it can hold for a fixed short period of time. A precise energy of zero for a precise time interval violates the uncertainty principle.
So empty space isn't sitting at zero energy. It can't.
It can't. It's jittering. It's vibrating around zero.
Yeah.
Frothing, seething. Pick your verb.
And this isn't a measurement problem, right? It's not that our tools are bad and we just can't detect the stillness.
No, absolutely not. This is one of the hardest things to grasp about quantum mechanics. The fuzziness is a fundamental property of reality itself. The universe is inherently uncertain at this level.
So even if you clear out all the matter, all the radiation, there's still something there.
The quantum fields are still there. The electromagnetic field, the Higgs field, all of them. You can't get rid of the fields. They are the fabric of space. And because of this uncertainty, those fields are constantly vibrating.
Okay, so we have energy fluctuating in empty space. It's buzzing. But Einstein taught us something pretty important about energy, right? The famous one, EMC22.
The most famous equation in history. Energy equals mass times the speed of light squared.
Which means energy and mass are two sides of the same coin. They are, for all intents and purposes, interchangeable.
Precisely. And this is where the pop-up universe comes into play. If you have energy fluctuations in the vacuum, and energy can become mass,
then the vacuum isn't just fluctuating with abstract energy, it's fluctuating with mass.
with particles.
This is the part that always sounds like science fiction to me. I mean, it just sounds impossible. You're talking about virtual particles.
Yes. Virtual particles. Ephemeral, fleeting, but very real.
So let's be very, very specific here. I'm looking at that empty box we talked about, the one we pumped all the air out of. What is actually happening inside it right now?
Okay. Picture a particle and its antiparticle. The
Right.
classic example is an electron and a positron, which is an anti-electron.
Okay.
Out of absolutely nowhere, the vacuum spontaneously borrows a tiny bit of energy from itself to create this pair. They pop into existence.
Out of nowhere, there's no source.
The source is the uncertainty of the quantum field itself. It's a loan from the universe's energy bank. So they appear, they exist for an incredibly brief moment, and then snap. They find each other, they get pulled back together and annihilate.
And they give the energy back.
They return the energy they borrowed back to the vacuum. The books are balanced.
So it's like a bank loan, a cosmic overdraft.
A very, very high-frequency, high-risk bank loan, yes.
And the uncertainty principle is the bank manager setting the terms of that loan.
That is a perfect analogy. The rule is the more energy you borrow, which means the heavier the particles you create, the faster you have to pay it back.
So you can make a big, heavy particle.
You can borrow enough energy to make, say, a top quark and an anti-top quark, which are incredibly massive.
Yeah.
But you might only have a trillionth of a second to exist before you have to annihilate and pay the debt.
That seems incredibly convenient. I have to be honest. Hey, these particles exist, but they disappear so fast you can't possibly see them. It feels like a mathematical trick. Like some physicists had a bookkeeping error in their equations and just gave it a cool name to cover their tracks.
Well, those were
Yeah,
virtual particles. Don't worry about them.
exactly.
And that is the healthy skepticism everyone should have. It sounds like a cheat code for physics, a fudge factor. But here's the thing. They are absolutely real. They are not just math. We have physical, experimental proof that they are there and that they have consequences.
Wait, give me the smoking gun. Because if they disappear in 10, 21 seconds or less, how in the world are we seeing them?
We don't see them directly, you're right about that. We see their footprints. We see the effects they have on the real particles we can see. And the clearest footprint of all is found in the simplest atom there is, the hydrogen atom.
The classic, one proton, one electron orbiting it.
Right. Now think about that electron orbiting the nucleus. In the old classical view, that electron is just a simple negative point charge. It's a lonely dot moving through a true void.
Sure, simple.
But in the quantum world, that electron is moving through this mosh pit of virtual particles we just described, this seething foam.
The vacuum is buzzing all around it.
Exactly. Now, the electron is negatively charged. The vacuum, meanwhile, is constantly popping with these virtual electron-positron pairs. The positive virtual positrons in that foam get attracted to our real electron.
Opposites attract.
And the negative virtual electrons get repelled. They're pushed away.
So the vacuum is reacting to the guest in the room.
It creates a crowd around it. It forms a polarized cloud of virtual particles that swarms around the real electron. And this cloud actually shields the electron's charge. It screens it.
Wait. So the charge of an electron that we measure isn't its real fundamental charge?
Correct. When we measure the charge of an electron from a distance, what we're actually seeing isn't the bare electron. We are seeing the electron plus this fuzzy, polarized cloud of virtual particles that is dampening its effect.
So the naked electron is actually stronger?
Much stronger. But we can never see it naked. We always see it clothed in the vacuum.
That is wild. It's like a celebrity trying to walk through a crowd of paparazzi. You can't see the person clearly, you just see this chaotic entourage moving with them.
That's a perfect analogy. And we can measure this entourage effect. It subtly changes the energy levels of the electron in the hydrogen atom. It's an effect called the Lamb shift.
And we can measure that shift.
We can. Or we can look at something called the magnetic moment of the electron. Basically a measure of how magnetic it is.
And how precise is this? This is where the proof comes in.
This is it. When we calculate what the magnetic strength of an electron should be using just simple quantum mechanics, without the virtual particles, we get a number, a very precise number.
Okay.
But when we go into the lab and we measure it, the experimental value is slightly different. It's a tiny bit stronger.
And the difference matches the effect of the cloud.
To an astonishing, almost unbelievable degree. When we use the full theory of quantum electrodynamics, QED, to calculate the influence of that virtual cloud, the theoretical prediction matches the experimental measurement to parts per billion.
Parts per billion.
It is often cited as the most precise and successful prediction in the entire history of science.
Wow. So if virtual particles were just a math trick, that calculation would be completely wrong.
It would be completely off. It wouldn't even be close.
Yeah.
The fact that it matches so perfectly tells us that the vacuum is alive, that cloud is real. You, me, the chair you're sitting on, every single electron in our bodies is walking around with its own little ghost entourage from the vacuum.
Okay, I'm sold on the atoms. But that's all microscopic. It's tiny. Is there any way to see the force of nothing on a scale we can actually, visualize? Can nothing actually push a physical object?
It can. And this brings us to one of my absolute favorite phenomena in all of physics, the Casimir effect.
This was discovered theoretically back in 1948 by Hendrik Casimir, right?
Yes. And at the time, people thought it was just a bit of a mathematical curiosity. The setup itself is deceptively simple. Imagine you take two metal plates, perfectly flat, perfectly reflective, and completely uncharged.
So no electricity, no magnetism?
None at all. You put them in a perfect vacuum and you place them incredibly close together. We're talking micrometers apart.
Okay. So, two neutral plates floating in the dark. Logic says they should just sit there. They have no reason to move. Nothing should happen.
Classical logic says nothing should happen. But Casimir did the math, he included the quantum vacuum, and he calculated that they would actually be pushed together. An invisible force would slam them shut.
Why? If they aren't magnetic, what's pushing them? Where does the force come from?
It's the vacuum itself.
Yeah.
The pressure of the void. To understand why, we have to stop thinking of these virtual particles as little balls for a second and start thinking of them as waves. Quantum mechanics says every particle is also a wave.
Right, the old wave-particle duality. I'm with you.
So, in the open space outside the plates, virtual waves of any size, any wavelength can exist. You can have big, long, rolling waves, tiny, short, choppy waves. Everything fits. The ocean's wide open.
Right. Unlimited possibilities.
But between the plates, it's a tight squeeze. You've created a boundary. It's like a guitar string. You can only play certain notes, certain wavelengths that fit perfectly between the two ends.
Ah, I see. You can't fit a wave that's bigger than the gap between the plates.
Exactly. You have physically excluded all the big, long wavelength virtual particles from the space between the plates. You've filtered them out.
So now you have an imbalance.
A huge imbalance. You have a full vacuum pushing on the plates from the outside. All the possible waves are banging against them. And you have a restricted vacuum pushing from the inside. Only the small waves that can fit.
So there's more pressure from the outside.
It's a radiation pressure difference exerted by nothing. There is literally more stuff popping in and out of existence and banging against the plates from the outside than from the inside. So the net effect is a force pushing the plates together.
That is actually somewhat terrifying. That empty space exerts real physical pressure. If you can exclude enough of it, it will crush you.
And we've measured it. It took a long time. The force is incredibly tiny and hard to detect. But in the 1990s, it was confirmed definitively. It's a real force. And, for modern engineers, this isn't just a fun theory.
Oh, how so?
Think about nanotechnology or MEMS microelectromechanical systems. These are tiny little machines, gears, and switches the size of dust motes.
Like the accelerometer in my phone that detects when I turn it.
Exactly that. When you build machines that small, the parts are incredibly close together. And for years, engineers found that sometimes these tiny parts would just stick. They would clamp together for no apparent reason and get stuck.
They called it stiction.
Stiction. And a big component of that stiction is the Casimir force. The vacuum is literally trying to weld your machine together. So you have to design your phone to actively fight against the pressure of the void.
So nothing is now an engineering constraint on our technology.
It absolutely is.
Okay, so we've established the vacuum is energetic, it's buzzing, it's real, it pushes plates around. But this leads to a massive, massive problem, doesn't it? I've heard this referred to as the vacuum catastrophe.
Oh, yes. The cosmological constant problem. This is where this beautiful, elegant theory crashes headfirst into reality and explodes in a ball of fire.
Let's get into this. We know there's energy in the vacuum. You called it zero-point energy.
Right. 0 point just means the lowest possible energy state. As we said, thanks to Heisenberg, it's not zero. Now, if you take quantum field theory seriously, you should be able to calculate how much energy is in, say, a coffee cup's worth of empty space.
You just sum up all those fluctuations.
You add up all the virtual particles, all the waves, all the jitters from all the different fields.
Okay.
And when physicists do this, they get a number, a truly mind-bogglingly, astronomically huge number.
How huge are we talking?
Well, let's put it in context. Einstein told us energy has mass, and gravity pulls on mass. So if the vacuum is full of this enormous amount of energy, it should have an enormous gravitational pull.
Right, it should weigh something. A lot.
An incredible amount. If the vacuum really contained the amount of energy the theory predicts, space itself would have so much mass energy that it would have instantly crushed the entire universe into a black hole fractions of a second after the Big Bang.
Okay, well, looking around, I can confirm that did not happen. I'm not currently spaghettified. The universe is still here.
And not only is it here, it's expanding. In fact, observations of distant supernovae tell us it's accelerating. The expansion is speeding up.
And that's driven by dark energy.
Which is, for all intents and purposes, the measured weight of the vacuum. It's the observed energy density of space that is pushing the universe apart.
So we have the theoretical weight, what the math says the vacuum should weigh, and we have the measured weight, what the telescopes say it actually weighs. What's the difference?
The discrepancy between the theoretical prediction and the observed value is about 120 orders of magnitude.
I'm sorry, did you say 120, as in a 1 with 120 zeros after it?
I did. A 1 followed by 120 zeros.
That is, I don't even have an analogy for that. If I was an architect and I calculated the load-bearing capacity of a bridge and I was wrong by 120 orders of magnitude, I wouldn't just be fired, I'd be arrested. The bridge wouldn't just collapse, it would turn into a singularity and devour the planet.
You're not wrong. It is spectacularly, epically bad. It is often called the worst theoretical prediction in the history of physics.
So, why do we still trust this theory? If the prediction is that catastrophic, why haven't we thrown the whole equation in the trash?
That is the million-dollar question, or trillion-dollar question, because the theory works perfectly everywhere else. That's what drives physicists crazy. It gives us the Lamb shift to parts per billion. It predicts the Casimir effect. It's the foundation of the standard model of particle physics. It works for lasers, for semiconductors. But when you apply it to the universe as a whole, it breaks. completely.
So the vacuum works perfectly in the lab, but fails spectacularly in the cosmos.
Exactly. Some physicists think there's a cancellation mechanism we haven't found, some deep, undiscovered symmetry that cancels out most of that enormous energy, leaving just the tiny, tiny residual bit we see as dark energy. Others think our understanding of gravity at quantum scales is just fundamentally wrong. But for now, it remains one of the biggest, most embarrassing unsolved mysteries in all of science.
It's fascinating that the thing holding the secrets to the entire universe is the empty space right in front of our faces.
And it gets even more dramatic, even more strange, when you take this buzzing vacuum and you put it next to the most extreme object in the universe, a black hole.
Ah, okay. Stephen Hawking territory.
Yes. In the 1970s, Hawking used this very concept of the quantum vacuum to turn our entire understanding of black holes completely upside down.
Before this, black holes were just cosmic vacuum cleaners, right? They're the ultimate eaters. Nothing escapes.
Correct. The event horizon was a point of no return, a one-way door into oblivion. But Hawking asked a simple question. What happens to the vacuum fluctuations right at the edge, right at the doorframe of the black hole?
The cliff's edge.
Precisely. Imagine one of our virtual particle pairs,
Yeah.
an electron and a positron, popping into existence exactly at the event horizon.
Okay. Usually they'd just snap back together and vanish in a flash.
Usually. But what if, in that tiny sliver of time they exist, one of them falls into the hole and the other one stays just outside?
They get separated. The cosmic divorce of the century.
The ultimate separation.
Yeah.
The one inside is captured. It's gone forever. The one outside is now alone. It has no partner to annihilate with.
So it can't vanish. It's been orphaned.
It can't vanish. To conserve all the laws of physics, like momentum and energy, it has to become real. It gets promoted from virtual to real. And it zips away from the black hole out into space.
So to an observer far, far away, it looks like the black hole just spit out a particle.
Exactly. It looks like the black hole's glowing. It's emitting radiation. This is Hawking radiation.
But wait a minute. Energy isn't free. We established that. You said the virtual pair borrows energy from the vacuum. If they don't annihilate, the debt isn't paid back to the vacuum. So who pays the bill for this newly real particle?
The black hole pays. This is the absolute genius of Hawking's insight. The particle that fell in. Because of the weird, intense warping of space-time at the horizon, it effectively has negative energy relative to the outside universe.
Negative energy. So the black hole eats a negative calorie.
That's a great way to put it. It eats a negative calorie. By swallowing that one particle with negative energy, the black hole's total mass energy decreases.
So the black hole is paying the energy cost for the particle that escaped and became real.
Yes. And that means the black hole is shrinking. It is slowly, incredibly slowly evaporating.
That is profound. We used to think black holes were these immortal monsters that would just sit there until the heat death of the universe. But because of the quiet, constant buzzing of the vacuum, they are mortal. They dissolve.
It takes an unfathomably long time for a big one, the Googleplex years.
Right.
But yes, they dissolve back into the vacuum from whence they came.
It's ironic, isn't it? The vacuum is the only thing that lasts.
Well, lasts is a strong word.
Oh no, don't tell me the vacuum can die too.
It's not that it dies, it's that it might change its mind.
I do not like the sound of that. Change its mind.
You see, we've been assuming that the vacuum state we live in, this specific buzz of empty space, is the bottom floor, the absolute lowest possible energy state, the ground state.
And it might not be.
We aren't sure. This brings us to the deeply unsettling concept of vacuum decay.
This is the cosmic horror part of our exploration today.
A little bit, yes. Think of a ball sitting in a deep valley. It's stable. It's not going anywhere. It stays at the bottom. We call that a true vacuum. It's as low as it can go.
Right. Stable. Safe.
But what if our universe isn't in the lowest valley? What if we are in a little dip, a small hollow up on the side of a much larger mountain? We feel stable. The ball isn't rolling, but there is a much deeper valley, a lower energy state further down. We call our current state a false vacuum.
So we are just living on a ledge thinking it's the ground floor.
We might be on a ledge. In classical physics, the ball stays put unless you push it. But in quantum physics, there is a spooky phenomenon called tunneling. The ball can, without any external push, spontaneously tunnel through the ridge and drop into the lower valley.
And in this analogy, the ball is the energy state of the entire universe.
The state of the fundamental fields that make up reality. Specifically, the Higgs field is the one we worry about. If our vacuum is only metastable, it could, in theory, spontaneously transition to that lower, truer energy state.
And what happens if that transition triggers somewhere?
It would start at a single point, anywhere. Maybe in a physics lab, maybe in a galaxy a billion light years away. A tiny bubble of true vacuum would form. And because it's a lower energy state, it is energetically favorable. It would expand.
How fast would it expand?
At the speed of light.
And what's inside the bubble?
The laws of physics as we know them would be rewritten. The fundamental constants of nature, the mass of particles like the electron, the strength of forces, everything would change instantly and violently. The chemistry that holds your body together would stop working. Atoms might not even be able to form in that new vacuum.
So it's not an explosion that destroys things, it's a reformatting of the universe's hard drive.
That's a perfect description. Matter as we know it would simply cease to be possible inside the expanding bubble.
And because it moves at the speed of light, we would have no warning, we wouldn't see it coming.
None whatsoever. We'd be having this conversation and then simply not be.
Okay, that is genuinely terrifying. How likely is this? Should I cancel my dinner plans for tonight?
No, keep your dinner plans. The universe has lasted 13.8 billion years without this happening. So the probability is likely incredibly, vanishingly low.
But
There's always a but.
But the math allows for it. It depends very heavily on the precise mass of the Higgs boson and another particle called the top quark. Our current measurements from particle colliders put us right on the edge. We seem to be in the metastable zone. So technically, we are living on the edge of a cosmic cliff.
Great. Well, while we are still here in this cozy false vacuum, let's maybe pivot to something a little less apocalyptic.
Yeah.
Because as abstract and cosmic as all this sounds, the quantum vacuum actually impacts the technology we use every single day, right?
Absolutely. It's not just for black holes in the hypothetical end of the world. It's in your pocket right now.
You're talking about semiconductor, right? The entire electronics industry, every computer chip, every smartphone, relies on understanding how electrons move through materials like silicon. But an electron moving through a silicon chip isn't moving through empty space. It's moving through a crystal lattice.
A solid block of atoms arranged in a grid.
And that lattice, that environment, modifies the vacuum. When a photon of light hits a semiconductor, it can excite an electron, leaving a sort of hole behind where it used to be. This electron-hole pair is itself an excitation that interacts with the vacuum fluctuations of the material.
The vacuum inside the rock.
Basically, yes. The optical properties of semiconductors, how they absorb and emit light, and how lasers work, are all deeply influenced by these vacuum interactions. If engineers didn't account for quantum field theory, our modern lasers and high-speed computer chips just wouldn't work the way they do.
And what about superconductors? Those amazing materials that carry electricity with zero resistance, zero energy loss.
That's another, even deeper vacuum phenomena. In a superconductor, below a certain temperature, electrons overcome their natural repulsion and pair up into what are called Cooper pairs.
Which is weird because electrons usually hate each other, like charges repel.
Exactly.
Yeah.
So how do they suddenly decide to pair up? They do it because the vacuum state inside the material has fundamentally restructured itself. The crystal lattice deforms in a way that creates a sort of attractive force mediated by the background vibrations.
So the background hum of the material actually coaxes them together.
The underlying symmetry of the vacuum breaks, allowing these pairs to exist and flow without resistance. So when you get an MRI or you hear about maglev trains or quantum computers, you are using technology that relies on a manipulated, restructured vacuum state. We are already engineering the void.
There's also this really weird concept called the Unruh effect. This one really messes with my head because it implies that nothing depends on how fast you're driving.
It's a beautiful, mind-bending connection between relativity and quantum mechanics. We usually think of emptiness as being absolute. If I see a vacuum, you see a vacuum. It should be objective.
Right. Zero particles should be zero particles for everybody.
But the Unruh effect says that if I am floating still in space, I see a cold, empty vacuum. But if you zoom past me, accelerating at a massive rate, you won't see a vacuum. You will see a bath of hot particles. You will feel warmth. You will see radiation.
Wait, so I see particles where you see nothing just because I hit the gas pedal.
Yes.
Where do the particles come from? They can't just appear.
They come from the vacuum fluctuations. Your intense acceleration pumps energy into the system from your perspective. It's like creating a sonic boom, but for the vacuum. You are ripping through the virtual particle foam so violently that your detector perceives those fluctuations as a real thermal radiation.
So temperature is relative. The very definition of empty is relative.
The vacuum of one observer is not the vacuum of another. That's the takeaway. If you could build a spaceship that accelerated hard enough, you could roast a chicken in what another observer would swear is cold, empty space, just from the friction of the vacuum itself.
That really challenges the idea of objective reality. The question, is there a particle there, has an answer that is, well, check your speedometer first.
Physics is full of these strange relative truths.
Let's talk about the strong force for a second. We talked about electrons and quantum electrodynamics, QED. We said the vacuum screens the charge. It surrounds the electron and makes it seem weaker from a distance.
Right, the entourage effect.
But I've read that for the forces inside the nucleus, for quarks and the strong force, the vacuum does the exact opposite.
It does. It's one of the strangest things. This is the realm of quantum chromodynamics, or QCD. And in QCD, the vacuum creates a phenomenon called anti-screening, or asymptotic freedom.
Anti-screening. So the vacuum doesn't hide the charge, it amplifies it.
It effectively does, yes. The virtual particles in the QCD vacuum aren't just quark-antiquark pairs. They're also gluons, the particles that carry the strong force. And gluons, unlike photons, can stick to each other. They carry their own charge.
They're sticky.
They're very sticky. Without getting bogged down in the deep mathematics, the net effect of this gluon-filled vacuum is that it acts like a tightening rubber band.
A rubber band? How so?
In QED, with electrons, the closer you get, the more you pierce that screening cloud, and the stronger the effective charge becomes. In QCD, with quarks, the closer you get, the weaker the interaction seems.
So when two quarks are right on top of each other inside a proton,
the rubber band is slack. They float around almost freely. This is asymptotic freedom. It won the Nobel Prize for Gross, Wilczek, and Pulitzer because it was so counterintuitive.
But if you try to pull them apart,
the vacuum fights you. As you pull two quarks apart, the rubber band of the vacuum stretches, and the energy in the field between them grows. The force gets stronger and stronger the farther you pull.
So it effectively locks them in. It's quark confinement.
It imprisons them forever. You can never, ever pull a single quark free from a proton, because to do so, you'd have to put an infinite amount of energy into the vacuum. Before you can do that, the rubber band snaps, but it doesn't release the quark. The energy you put into stretching it becomes so great that it's cheaper for the vacuum to just create a new pair of quarks out of thin air.
So you start with one quark, you pull, and you end up with two. You can never isolate one. The vacuum is the prison guard of matter.
It is the glue that binds the nucleus together. Without this specific, weird anti-screening behavior of the vacuum, protons and neutrons wouldn't hold together. Atoms wouldn't exist. We wouldn't exist.
So we've covered how the vacuum works now. It screens electrons, it binds quarks, it pushes plates around, it makes black holes evaporate. But what about the beginning, the ultimate origin story?
The Big Bang.
There's a theory that says the entire universe itself is just a vacuum fluctuation that got, well, a little out of hand.
That's essentially the core idea behind inflationary cosmology.
Can you explain that? How do you get everything from nothing?
In the very first fraction of a second, we think the universe underwent a period of hyper-accelerated expansion called inflation. But what drove it? The theory says it was driven by the energy of a quantum field, the inflaton field. It was a very high-energy vacuum state.
Okay. A supercharged version of the vacuum we have today.
Exactly. Now remember those tiny quantum jitters we talked about at the very start? The unavoidable fuzziness from the uncertainty principle?
The microscopic fluctuations.
During inflation, the fabric of space itself expanded so incredibly fast, faster than the speed of light, that those tiny, microscopic subatomic jitters got stretched. They were physically stretched from a size smaller than a proton to the size of a galaxy.
Whoa, so a quantum blip, a momentary energy fluctuation, became a galaxy.
It became the seed of a galaxy. Those fluctuations, stretched across the cosmos, created tiny differences in density across the early universe. Some spots were a little denser, some a little emptier, all because of a quantum roll of the dice.
And gravity took over from there.
Exactly. Over millions of years, the slightly denser spots pulled in more matter, eventually collapsing to form the first stars, galaxies, and the great cosmic web. The slightly emptier spots became the great voids between the galaxy clusters.
So if I look at a map of the large-scale structure of the universe, that web of galaxies, what I'm really looking at is a blown-up, fossilized picture of the quantum vacuum from 13.8 billion years ago.
You are. And we have incredible proof for this. We can look at the cosmic microwave background radiation, the baby picture of the universe. It shows tiny temperature fluctuations. The specific pattern of those hot and cold spots on the sky matches the mathematical predictions of quantum vacuum fluctuations perfectly.
That is heavy. We are literally made of frozen quantum noise.
We are. If the early vacuum had been truly still, truly empty in the classical sense, the universe would be a smooth, featureless, boring soup of particles. No stars, no planets, no us. The fundamental instability of nothing is the only reason that something exists at all.
There's also something called the Schwinger effect, right? Which is about, like, ripping matter directly out of the void here and now.
Yes, this connects back to that idea of creating something from nothing. The physicist, Julian Schwinger, predicted that if you could create an electric field that is strong enough, and I mean truly ridiculously massive, like 1018 volts per meter.
Which is a lot.
A lot more than we can currently make. But if you could, the field would be so strong, it would literally pull on the virtual electron-positron pairs in the vacuum, rip them apart before they can annihilate, and make them real.
Just by applying a strong enough field to empty space.
Yes, you provide enough energy to the vacuum with your field to pay the mass debt and pop. Real matter appears where there was none before. We haven't fully achieved this in a lab yet, but some of the world's most high-powered lasers are getting very, very close to that limit.
It's the ultimate alchemy, making matter from empty space.
It reinforces the modern idea that matter isn't really a separate thing in the vacuum. Matter is just an excitation of the vacuum. It's a persistent wave on that quantum ocean. You can't have the waves without the water.
This whole conversation, it really shifts the philosophical ground, doesn't it?
It absolutely does.
We usually think of creation as needing a builder, an external agent, someone to arrange the bricks and mortar. But this suggests that the bricks just appear spontaneously because the empty space refuses to be quiet.
Exactly. Nothing is unstable. In modern physics, you don't necessarily need a miracle to get a universe. You just need a quantum vacuum in time. The void is naturally fundamentally creative.
It's beautiful in a way. The universe breathes.
And there's one final frontier, a real bleeding-edge idea we should touch on. The idea that space and time themselves might not be fundamental.
What could be more fundamental than space and time?
The vacuum. Some modern theories, ideas from string theory and quantum gravity, suggest that space-time is emergent, that the connections, the quantum entanglement between different regions of the quantum vacuum are what actually stitch the fabric of space together.
So if you could somehow turn off the entanglement between the fluctuations,
space would fall apart. The very concept of distance might lose its meaning.
that is a lot to process.
It is. We are still learning. We still have the vacuum catastrophe to solve. We have the connection between the vacuum and gravity to figure out.
Yeah.
But one thing is absolutely settled. The box is not empty.
The box is alive.
The void is alive.
So the next time you look up at that night sky and you see that profound darkness between the stars, don't think of it as nothing. Think of it as a seething, boiling ocean of potential, buzzing with invisible energy, creating and destroying particles every billionth of a second, holding the core of your atoms together and pushing the galaxies apart.
It's the fullest, busiest place in the universe.
And here's a thought to leave you with. If space-time itself truly does emerge from the web of entanglement of the vacuum, as these new theories suggest, are space and time just illusions? Are they just a useful story our minds tell? A story created by the incessant crackling buzz of the void? Are we just surfing on the noise?
That is the question that keeps physicists up at night.
Thanks for this fascinating journey.
Pleasure, as always.